joined by team members Chaturi and Pooja. Today our topic is area concentration in extrinsic semiconductor.
Okay, before saying this topic, I will discuss about the previous topic that you guys understand this topic very briefly. So, as you all know, semiconductors are two types. One is intrinsic and intrinsic semiconductors, and two is extrinsic semiconductors. In intrinsic semiconductors, there are two types: N type and P type. Has like that only in extrinsic semiconductors also there are two types: N type and P type. Now we are discussing about N type semiconductors. In N type semiconductors, they are in the outermost shell of extrinsic semiconductors. There are five electrons. So in this question, the majority is not holes. The majority is about the electrons. First, I will draw this. Then you guys will understand more. This is valency band. In this valency band, they all are electrons. This is before applying the temperature. In conduction band, they all are holes. After applying some temperature, all electrons will go to that holes. And here, after applying temperature, I am saying the conduction bond will fill with electrons. And in the valency band, the holes will fill, because here all electrons will jump into the conduction band. So, in this N-type extrinsic semiconductors, as I said before, the majority is not in holes. The majority is electrons, because in N-type semiconductors, they are in the outermost shell. They are five electrons. So, to form a proper bond, the electron must be 4 in the outer shell, but one electron will be extra. So, the extra electron will be the majority of these electrons. So, in this band, the extra electrons will form here, like this. So, in this question, all electrons will jump. See, here is the form before applying the temperature. The electrons will be there in this question. So, after applying the temperature, first the electrons will move to these holes, and then this electrons. So we can neglect this, because electrons are majority here. The extra electrons will stay here in the form of EF, Fermi energy.
Kinda.
So this is what I said before. In N-type semiconductors, the donor level just below the conduction band. As I said, the conduction band is above the diagram. So the Fermi level is donor level, which is donates the electrons, is just below the conduction band. See, conduction just below the conduction band, the donor level. Let ED represents the energy of donor level, and ND represents the donor concentration. Let ND is called number of donor atoms per unit volume. The donor level is very nearest to the conduction band, hence the effect of valency band can be neglected. As I said before, we can neglect this valency bond, but we cannot neglect this valency bond completely. We can just maybe it will be neglected, but it does not neglect completely. So we will talk about these two. One is conduction band and another is Fermi energy. So that is the point. Concentration of electrons in conduction band is equal to the positive ionized donor per unit volume. The electrons and the conduction band holes will be equal. The density of electrons in conduction band. This is the formula which we derived from the third question. Like density of electrons in conduction band. This is the formula. N is equals to Nc expression EF minus EC by kBT. And this is also the expression from the same conduction band. As I said, where EF is the Fermi energy level and EC is the Fermi energy corresponding bottom to the conduction band. Fermi energy level means nothing but the electrons which stay, the extra electrons will stay. That is called Fermi energy level. And this is called energy, conduction of energy band. So you guys know the conduction band, this is what it. Number of valency per unit volume in donor level. In donor level, this is the formula and Nd into 1 minus F into Ed. F into Ed formula is 1 by 1 plus exponential Ed minus Ef by kBt. So here Nd represents density of donor level and 1 minus F into Ed represents the probability of absence of electrons in donor level and F into Ed represents the probability of finding an electron. Over.
From our equation, Nd into 1 minus F of Ed is equal to Nd into 1 minus 1 by 1 plus exponential of Ed minus Ef by kBt. We take the LCM. Nd into 1 minus F of Ed is equal to Nd into 1 plus exponential of Ed minus Ef by kBt minus 1 by 1 plus exponential of Ed minus Ef by kBt. You can see minus 1 and plus 1. We get Nd into 1 minus F of Ed is equal to Nd into exponential of Ed minus Ef by kBt by 1 plus exponential of Ed minus Ef by kBt. Next we neglect the exponential of Ed minus Ef by kBt in denominator. Neglect the exponential of equation ND into 1 minus f of ED is equal to ND into exponential of ED minus EF by KBT. Next, the number of electrons in the conduction band must be equal to the number of ionized donors. N is equal to ND into 1 minus F of ED. N is equal to ND into 1 minus F of ED. Next, N is equal to NC exponential of EF minus EC by KBT. Next, ND into 1 minus F of ED is equal to ND into exponential of ED minus EF by KBT. This is equation 1. Where NC is equal to 2 into 2 pi ND star Next, NC divided this equation exponential of this minus EF comes to left side, EF plus EF by KBT ND by NC. This minus EC comes to the right side, ED plus EC by KBT. Get equation exponential of 2EF by KBT is equal to ND by NC exponential of ED plus EC by KBT. Now we apply logarithm above equation. We have to take A, B, log exponential cancel. Next, 2EF by KBT is equal to log AB log A plus log B. Log of ND by NC plus log exponential get cancelled, ED plus EF EC by KBT. That's 2 by KBT, this divided. EF is equal to KBT by 2 log of ND by NC plus
into exponential of kBT by 2 log ND by NC plus ED plus EC by 2 minus EC whole divided by kBT. We take 2 as LCM and then n is equals to NC into exponential of kBT by 2 log of ND by NC into ND by NC plus ED plus EC minus 2EC by 2 whole by kBT. Now we take kBT as common. N is equals to NC into exponential of kBT whole 1 by 2 log of ND by NC plus ED minus EC by 2 kBT whole by kBT. Then kBT get cancelled. This is in the form of n log A is equals to log A whole power n. That is n is equals to NC exponential of log ND by NC power 1 by 2 plus ED minus EC by 2 kBT whole by ED minus EC by 2 kBT, and then exponential of A plus B is equals to exponent of A into exponent of B. Is equals to NC into ND by NC whole power 1 by 2 into exponential of ED minus EC by 2 kBT. Then n is equals to NC. This NC, when we take this to numerator, it becomes 1 minus 1 by 2, and then ND power 1 by 2 exponential of ED minus EC by 2 kBT. Then n is equals to NC power 1 by 2, ND power 1 by 2 exponential of ED minus EC by 2 kBT. As we already know, NC is now we have to substitute the value of NC in this equation. NC is equals to 2 into 2 pi kBT m E star by h square whole power 3 by 2. We have to substitute this in this equation. Then we get n is equals to 2 1 by 2 exponential of ED minus EC by 2 kBT n is equals to 2 nd whole power 1 by 2 2 pi kBT m e star by h square whole power 3 by 4 exponential of ED minus EC by 2 kBT. This is the expression for carrier connection in n-type semiconductors. Pooja will continue.
Okay, as she said, this is the expression of n-type semiconductors. From equation 2, as I said before, starting this section, T is equals to 0 Kelvin. So EF and Fermi energy is equals to ED plus EC by 2. So this is the diagram which I draw before starting this. So this is conduction band and this is the valency band. As I said, all the electrons in this n-type semiconductors, electrons will store here. As I said before, from this to this, they will exchange from this band to this band. This is called n-type extrinsic semiconductor.